Asynchronous replication, combined with the fact that you can read from any replica, including followers, can be dangerous. A client could very easily read from a follower and get the wrong answer, since the follower might be out of sync with the leader. For example, suppose that the score of a sports game is 3-3 at 2:30 p.m. The leader and the follower both agree on the scores at that point. But then suppose that a point is scored at 2:31 and it's now 4-3. The leader gets the update and starts sending it to its followers. Then at 2:32, a client reads from a follower. That follower hasn't heard about the new score yet, so it still reports 3-3. But another client happens to read from the leader at the same time and sees the real score, which is 4-3. So now our user is seeing completely different results just because of the randomly chosen replica that they read from. This scenario is known as replication lag, and it leads to inconsistencies in our systems. If you run the same query on different replicas, you might get different answers, which will be very confusing for everyone involved. The good news, though, is that this lag won't stick around forever. Eventually, all the followers will get the news and update themselves. To go back to our sports example, by 2:40 p.m., all of the followers should have gotten the update and should be reporting a score of 4-3. In other words, the followers will all eventually become consistent with the leader. There's eventual consistency again. One compromise is called read after write consistency. It aims to cover the most frustrating type of inconsistency that eventual consistency causes, which is when a user writes something, such as updating their bio on their profile page, and refreshes the page, only to see that it's gone because they now read from a different follower. In these cases, we want to ensure that a user who writes something will not see any inconsistency when they go back to read that same thing later. Hence the name read after write consistency. There are many possible approaches to implement this strategy. A simple one is that if we know something can only be written by a single user, then when that user goes to read the page, we always serve it from the leader to ensure freshness. In this case, you're the only one who can edit your own profile page, obviously. So if you go to view your profile page, it'll always be served from the leader. If anyone else views your profile page, or if you view somebody else's profile page, it'll be served from a follower. This is a clever strategy, and it can be scaled to work when a handful of users are able to edit the page, but it doesn't really work beyond that. A different strategy is that the client can remember when it last posted a write to a certain page. When it reads that page and gets data back from some particular replica, the client can check when that replica was last updated. If the replica's last updated date is too old to have gotten the client's most recent write, the client will ask another replica, or just wait till this replica has caught up. For example, if you write to a page at 3:15 and then go read that page and find that the replica was last updated at 3:10, you can be sure that it will not include your update, which was at 3:15. You'll have to ask for another, fresher replica. Another potential way to look at eventual consistency and replication lag is that we don't want the user to be able to go backward in time. If you see that the score is 4-3 and then you refresh, you shouldn't start seeing that the score is now 3-3. That would be confusing, and it would appear like you were traveling backward in time. The backward in time problem happens when the user first reads from a replica that was updated recently, and later reads from a replica that was updated before that. So we could enforce a rule that if a user reads from replica A, they can never get data from a replica that was last updated before A was last updated. So if replica A was last updated at 12:20, replica B at 12:15, and replica C at 12:25, and the client reads from replica A, then they can no longer read from replica B. They can only read from A or C going forward. This way to the user, it appears that time is flowing monotonically forward. It may not move smoothly into the future, and it may even appear frozen at times, but at least it's not going backward. A dead simple way to implement the monotonic read strategy is to always make sure the user reads from the same replica. If you read from replica A once, you will always read from replica A going forward. Since replicas can't go back in time or undo updates, this way the user will never go back in time, satisfying our monotonic constraint. Directing the user to the same replica every time is pretty easy to do. You could pass their IP address or user ID through a hash function and use that to determine their assigned replica. As long as those inputs stay consistent, and their user ID usually does, their assigned replica will also stay consistent. This monotonic read strategy still has its downsides though. You need to figure out what to do if the user's assigned replica goes down. you'll need to choose a new replica and consistently reroute the user to that replica every time they load a page. So, though they have their drawbacks, monotonic reads and read after write consistency are both good options for overcoming the problems of replication lag. As always, confirm that replication lag is actually a problem for you before you implement any of these optimizations. But if it is a problem, these should prove to be useful tools.